A perfectly configured firewall is useless if the hardware it runs on has a structural flaw. High-level protective controls can be completely bypassed by malicious actors if the underlying foundation is compromised. To understand true system security, we have to look past the software and examine computer architecture at the logical level. This is where the physical design of components translates directly into security capabilities. This reliance on underlying systems introduces the principle of shared responsibility. Organizations do not operate or build their IT infrastructure in a vacuum. Because modern businesses rely heavily on off-the-shelf operating systems, common programming languages, and shared communication protocols, they are automatically integrated with the vulnerabilities of that global ecosystem. Every tier of an organization carries a portion of this burden. The regular employee executing daily tasks, the CISO designing the network, and the auditor monitoring the environment all share the responsibility for operating securely within this hardware foundation. True system security is not a layer you can simply bolt on top of a network. It requires strict logical controls baked directly into the physical processing components to prevent malicious bypass. Despite the complex outputs of modern computers, the central processing unit, or CPU, can only perform a highly limited set of computational and logical operations. This restriction is intentional, allowing the CPU to execute those specific instructions at blazing speeds. As processing power increased over time, users demanded features that required systems to manage multiple functions simultaneously. This created the engineering challenge of doing two things at once. The earliest solution was multitasking. In a single core system, the operating system simulates simultaneous execution by carefully sequencing the commands sent to the CPU. It works exactly like juggling. Your hands touch only one ball at any given instant, but the rapid coordination of movements keeps all three balls in the air. A similar approach is multiprogramming. Here, multiple processes are serialized into a batch. When one process pauses to wait on a peripheral device, its state is saved into memory, and the next process immediately jumps into the CPU for its turn. This method causes significant delays for completing any single task. However, across all processes in the batch, the total time required to complete every task is reduced. Modern hardware solves the concurrency problem physically. Most systems today rely on multi-core hardware, where a single physical CPU chip contains multiple independent execution cores operating simultaneously. Scaling this up gives us multiprocessing. A multiprocessor system harnesses the power of more than one physical processor to execute a multi-threaded application. In these environments, engineers often use a technique called affinity. Affinity is the practice of dedicating a specific process or execution thread to a specific CPU or core to optimize performance. To reduce the heavy overhead of constantly switching between active processes, systems use multi-threading. This permits multiple concurrent tasks to operate within a single parent process, making execution far more efficient. While these concurrency methods maximize the efficiency of physical hardware, they introduce a critical security risk. Multiple, potentially untrusted processes are now sharing the exact same memory space and processor cycles. Because processes share hardware, the runtime environment must integrate security controls that isolate the operating system's integrity from active user applications. This is a diagram of the four-layer protection ring model. It illustrates how isolation is achieved through concentric layers of privilege that enforce strict memory segmentation. The innermost layer is ring 0. It possesses the highest level of privilege and can access any resource, file, or memory location on the machine. Ring 0 is occupied by the kernel. The kernel is the resident component of the operating system that always remains in memory, to run on demand, giving it the power to preempt code running in any other ring. Moving outward, rings 1 and 2 operate in a slightly privileged space. This area is reserved for non-resident operating system components, input-output drivers, and system utilities. The outermost layer is ring 3, which contains standard user-level programs and applications. Ring 3 operates in what is called the problem state, whereas the inner rings operate in the supervisory state. In the problem state, privileges are low, and all access requests must be explicitly checked against credentials for authorization before they are granted. This creates a mediated access model. Programs in higher-numbered rings cannot access resources directly. If an application in ring 3 needs a system resource, it must generate a system call, asking a handler in a lower numbered ring to perform the service on its behalf. In practical application, many modern operating systems simplify this 4-ring structure into just 2 divisions: kernel mode for rings 0 through 2 and user mode for ring 3. The ring model acts as the structural boundary that prevents a malicious user application from directly rewriting the operating system's critical memory. Physical memory segmentation is only half the equation. The operating system must also enforce temporal boundaries to manage how processes actually line up for execution in the processing queue. This flowchart shows the life cycle of an executed process. Operating systems grant CPU time only in fixed increments called time slices. Depending on where a process is in its execution, it exists in one of several distinct states. First is the ready state. A new or unblocked process waits in the queue here until it is scheduled for execution and the CPU becomes available. Once the CPU is clear, the process transitions to the running state. It executes its instructions on the processor until it finishes its task or its allotted time slice expires. If the time slice expires before the task is complete, the operating system forcefully pauses the process and returns it to the ready queue. This prevents any single program from monopolizing the CPU. If a running process pauses to wait for an input or output request to be serviced, it drops into the waiting state. Once the I/O is complete, it unblocks and moves back to the ready queue. There is also an invisible supervisory state. This elevated privilege mode is triggered when a process needs to perform restricted actions, like modifying system configurations or installing new device drivers. Finally, when a process finishes or is terminated, it enters the stopped state. Here, the operating system recovers all the memory and hardware resources previously allocated to that process, so they can be reused. Strictly enforcing these execution states and time slices guarantees that no single process can hoard hardware resources or bypass security authorizations during its run cycle. The strict logical boundaries enforced inside a single CPU chip must be mirrored externally in the way enterprises handle their data across the globe. This brings us to data sovereignty, the principle that digital data is legally subject to the laws of its originating country. This differs from data localization, the physical mandate that data must be stored and processed on servers located within that specific jurisdiction's borders. Adhering to these geopolitical macro boundaries directly dictates how systems engineers must architect their physical storage and deploy their cloud infrastructure. Operating safely across these borders requires constant communication about emerging risks. This is handled through Automated Indicator Sharing, or AIS. AIS is an initiative that facilitates the open exchange of cyber threat intelligence between governments and the private sector at machine speed. AIS relies on STIX and TAXII. STIX is a standardized language for expressing structured information about cyber threats, while TAXII is a set of protocols defining how that structured threat information is actively shared over the network. Security architecture is an unbroken chain of shared responsibility. Defending a network means enforcing execution states at the microscopic hardware level, while simultaneously deploying automated threat intelligence across global legal boundaries.